And again, make sure you ask questions. If you have any questions, or you need me to slow down or speed up or move on, just feel free to let me know. The more interaction, the better. Then I feel like I'm actually conversing with someone other than just my computer screen. All right, so today we're going to talk about the Earth specifically. So the title here says the Earth and the universe. We'll get to kind of space science eventually, but today especially we're going to focus on just kind of the geology of the Earth, right? And so we're going to start with talking about plate tectonics and kind of the theory of plate tectonics. So the Earth, and we'll get to the layers of the Earth eventually today, but the outer surface of the Earth essentially is, made up of the layer we call the crust, and the crust is broken apart into these plates that fit together kind of like a jigsaw puzzle, right? And the theory of plate tectonics is that these plates float on the surface of the Earth, and they move slowly over time, right? So anywhere from about 1/2 inch to 4 inches a year, depending on the plate and the type of boundary or margin that plate has. Right? So there is lots of evidence to support the theory, right? The spreading of the seafloor and some of the measurables, right? Like you can figure out, that Mount Everest is getting incrementally taller every year, right? And things like that. So we know there's some amount of motion to the crust of the Earth, right? Or the outer layer of the Earth. So when we're talking about plate tectonics, the big thing that we want to talk about is plate boundaries, or in other words, where one plate ends and another plate begins, right? So if we were talking about it in terms of a jigsaw puzzle, it would be, where the pieces fit together, right? And so just to give you, and I'll come back to this slide in just a minute, but if we look at this picture here, right, this is essentially a map of all the plates on the Earth's crust. Okay, so that's kind of what I'm talking about. And when I talk about plate boundaries or plate margins, those mean the same thing. I'm talking about right here, right, where one plate butts up against the other. Okay, so with that said, let's go back. There are essentially 3 different types of plate boundaries. So the first, and we'll just kind of go through them here, is a constructive or divergent boundary. Okay, so and the reason that they are referred to as constructive and divergent, they're kind of 2 different terms for the same thing. Is so, and I'll explain it here in just a second. First is, so divergent. To diverge means to move away from or pull apart, right? So a divergent plate boundary is where you have 2 plates moving away from each other, okay? And so the reason that it's also referred to as constructive is because if you have 2 plates that are moving away from each other, what is filling that gap? It's not just there's not an empty void there. It's actually being filled with new crust. In other words, molten rock is coming up from the layer beneath the crust, right? And actually generating new crust. So the reason it's called constructive is because it's an area where 2 plates are moving away. That's why it's diverging, but it's constructive because new crust is formed, okay? So usually that happens, mid-ocean boundaries are typically divergent boundaries because as you pull away, typically what happens is the plates sink and pull away. So you get ocean troughs. And that's, again, the reason why the oceans are shaped the way they are is often because of the way that those plates are pulling apart and the ocean's actually getting bigger and deeper, right? On the flip side of that, the opposite of divergent is convergent, right? So if divergent boundaries are boundaries that are plates that are moving away from each other, convergent plate boundaries are where you have two plates running into each other. Right? And the reason that those are referred to as destructive plate boundaries, because unlike constructive plate boundaries where you have new crust forming, at convergent or destructive boundaries, you have crust being destroyed, right? So the Earth only has a finite amount of space in terms of if we were to, sorry for using a math term, right? But if we were talking about the surface area of the Earth, right? In other words, the area of the entire outer edge of the Earth, right? If we were to measure that, that surface area doesn't get bigger or smaller, right? There's only a certain amount of space on Earth, right? And so if there are areas where crust is being created, in other words, new crust is forming, then there has to be an equal amount of crust being destroyed, okay? So think about it that way. And whereas divergent or constructive boundaries typically happen in the ocean, not always, but typically, right? Convergent or destructive boundaries typically happen where you get either mountains or you get oceanic plates butting into continental plates, right? So that's often why you'll see mountain ranges on the coast. And so the one thing, and I don't see it listed here, and I can't remember the different terms, but when you talk about convergent boundaries, there are a couple things that can happen, right? And I think there are terms for them, but I'm not going to pretend to know what they are at the moment, right? But when two plates hit each other, one of two things typically happen. One is they bend upward and form mountains, right? So anytime you have, not anytime, but the vast majority of big mountain ranges on Earth are created from this phenomenon, where you have two plate boundaries crushing into each other, okay? So the other thing that can happen, and this typically happens where you have a thinner ocean crust and a thicker continental crust, is sometimes when the two hit, the thinner ocean crust just gets pushed underneath and actually gets like recycled back into the lower levels of the Earth, right? And so you don't necessarily see mountains there, but you see that the thinner plate slowly shrinking because it's getting pushed or shoved underneath, right? So when you have convergent boundaries, either of those things happen. Either they both hit and shoot up, or one gets pushed under the other. Okay? And then the last type of plate boundary we call a transform boundary or a conservative plate boundary. That's where new crust is not being created or destroyed, right? And the plates are sliding alongside one another. So they're not directly hitting each other. They're not pulling away from each other. They're like sliding on by each other, like this, right? And a good example of that would be where you see big faults, or even like the state of California. There is a giant fault. The San Andreas Fault runs right down the middle of California. And that's because half of California is on the North American plate, and half of California sits on the Pacific plate. And there are two different plates moving in two different directions. And so that's why California is slowly being ripped apart. And not surprisingly, that's why California has so many earthquakes. Right? Transform boundaries are the most common type of boundary when you talk about areas where earthquakes occur a lot. And that's just from the amount of friction from those plates sliding back and forth. And then the last thing on this slide before I move on is you can see down here it says Pangea megacontinent, and that's just a theory that if you take plate tectonics and the theory of all these plates moving around and you kind of rewind time, eventually you get back to where the plates look different. And actually, the mass of land on Earth was just one big continent that is slowly, as the plates have drifted, the different continents have separated, different continents have collided, and now we have this different shape of continents than we did, millions and billions of years ago, right? So let's go back to this picture here because it's just a better visual of kind of what we're talking about. And just real briefly, like when we talk about Pangea or a megacontinent, right? Some of the theory behind that is, the way that a lot of the continents seem to fit together, right? And it's a theory because it's not something we can decidedly prove is true, right? So when I use the word theory, I'm talking about things that are accepted, not truths, but accepted likelihood, maybe. It's a likely possibility that was the case, right? But like if you look at, the east coast of South America and the west coast of Africa, you can kind of see how at one point they maybe fit, right? So again, getting back to plate tectonics, you can see all these different arrows, and the arrows represent the direction that these plates are moving in general. So you can see in the middle of the Atlantic Ocean, plates are pulling away from each other. You've got the North American plate and the African plate and the Eurasian plate and the South American plate, and they're all pulling away from each other. So the Atlantic Ocean is getting slowly, very slowly, bigger and bigger every year, right? Because those continents are drifting further apart, right? An example of a convergent plate boundary, right, where you have two plates coming together. You could see this Nazca plate and the South American plate directly colliding. You can also see the Australian plate here, and the Eurasian plate colliding to each other. And it just so happens, right here at the northern edge of India and the southern edge of China, and along this west coast of South America, you happen to have our two biggest mountain ranges, right? The Himalayas and the Andes. And that's from those plates crushing into each other. And then I mentioned the transform boundary up here in California. It doesn't have the arrows, but again, you have one plate that's sliding past another plate and kind of ripping that Earth apart slowly over time, right? So let's see here. I want to go from here. Let's see what we do. All right. So the last thing before we kind of look at some practice questions would be the structure of the Earth, right? So the plates all exist in this outermost layer, which is called the crust, right? So the crust is broken up into these plates. And the typical makeup of the crust is it's solid, right? It's made up of granite, basalt, and all other types of rock, right? So solid rock. And it's anywhere from 3 to 40 miles thick, right? And typically under the ocean crusts are much, much thinner. So the ocean is where you see the crust more in the 3-mile thickness. And under the continents is more where you see the 40 miles. All right. So like below us right now is probably somewhere between, somewhere around 40 miles of solid, right? That was it. Once you get underneath the crust, the next layer down is called the mantle. And the mantle is molten or melted, and it's in a semi-liquid state, almost like Jello, the way I've had it described to me, right? It has characteristics of a solid, it has characteristics of a liquid, but it's less stable than just a solid rock. And so the reason that the Earth's crust shifts around a little bit is because you have this solid rock sitting on top of this jello-y, molten material, and it's unstable. And so that's why it's kind of, that's why we use the word floating, right? It's because it's kind of acting like it's floating on top, right? And so the mantle is made up of typically silica, which is one of the elements we've talked about, and it's metal-like, it's not metal, and other types of metals, metal materials. So we're talking about various types of metals and silicon, right? Make up the mantle. And the mantle is about 1,800 miles, right? So the crust, I mean, 40 miles seems like a lot, but relative to the diameter of our Earth, right? 40 miles is very little, right? The mantle is much, much, much thicker. The thickest section of the Earth is the mantle, about 1,800 miles. Once you get all the way through the mantle, you get to the core of the Earth, okay? And the core of the Earth is made up of iron, right? The outer core is liquid iron, because as you go further and further into the core or into the Earth, right, temperature rises and pressure also rises. Pressurized and very hot conditions. So the outer core is actually in a environment that's so hot that we have iron in a liquid state, so very, very hot. And that core is about 1,400 miles thick, so really, really thick. So when you think of the core, sometimes you think of it being small, but the core is pretty big. And again, it's liquid iron. And then when you get to the inner core is actually solid iron, and it's about 800 miles. And so one thing to think about is, why is the inner core solid and the outer core liquid? Because again, as you go deeper and deeper in the Earth, it gets hotter. So it doesn't make a lot of sense that the inner core would be solid and the outer core would be liquid. Right? You'd almost think maybe it'd be the other way around, right? Because if it's even hotter, then it should be liquid. But the reason that the inner core is solid doesn't have to do with temperature, it has to do with pressure. Because there is such an intense amount of pressure on the core of the Earth that when you get to the inner core, the molecules in that iron, even though they're super hot, have just been pressed together so hard that they're essentially frozen in place and suspended. And so if you were in class when we talked about states of matter, right, we talked about the particles in a solid being tightly packed, kind of vibrating, but not moving around, whereas in a liquid, the molecules have a little more space and they kind of move and float around. But because the core of the Earth has so much pressure, those molecules aren't allowed to move around, even though it's really hot. And so you get solid iron in the very center of the Earth. Okay, so the GED book actually has a little picture of this. So I'm going to share it, and then I'm going to pull up practice questions on the same page. We'll do just a few. So here's the picture I was talking about. Right? And so this is like a piece of the pie, right? A fourth of or a quarter of the Earth. So the crust, again, is that thin outer layer of solid rock, followed by a thick layer of molten mantle, which was silica and other metals and metalloids. And then the core, both the outer core, which was liquid iron, and the inner core, which is solid iron. And so you have both of those things going on in the core. So that's kind of the very basic structure of the Earth, right? So if we take a look at some of these practice questions, and let's see, we're doing fine for time. We'll just kind of see what we get to. And if you feel like answering these questions in the chat, you can, or if you just want to do them amongst yourselves, that's fine too. So now let's look at number one. So number one says, what does the theory of plate tectonics explain? A, changes in the Earth's crust. B, changes in the Earth's mantle. C, changes in the composition of Earth's layers. Or D, why there is such extreme heat and pressure in the Earth's core. Again, remember plate tectonics, what we're talking about. We're talking about just what layer of the Earth. Plate tectonics is only referring to stuff going on in the crust. Okay? So B, changes in the Earth's mantle. Doesn't make sense. C, changes in the composition of Earth's layers. Right? Plate tectonics isn't talking about all the layers. And D, it's not talking about the extreme heat and pressure in the core. Even though that's a true statement, it's not, plate tectonics aren't dealing with that. So the answer for this one is just A, changes in Earth's crust. Okay, so let's look at number 2. Number 2 says, fill in the blanks with the options below. One similarity between the Earth's inner and outer cores is that both blank. So let's just maybe go through this kind of one step at a time. So for the first blank, here are our options. Consists primarily of iron, consists primarily of granite, consists primarily of silicon. Remember, the Earth's inner and outer cores are both made up of iron. Right? So consists primarily of iron. That's our first one. And then it goes on to say, although the two are different because the inner core blank, while the outer core blank. So here are our options. So for 2, we have, and these are the same, 2 and 3, right? Mostly gaseous, mostly liquid, mostly solid. Again, mostly gaseous, mostly liquid, mostly solid. Remember, the inner core is the innermost one, remember? And remember, the pressure is greatest there, so the inner core is mostly solid, while the outer core is mostly liquid. Okay? So there you go. I kind of walked us through that one maybe a little bit too quickly, so hopefully you had a chance to actually try that one on your own. I'll let you look at number 3 and give a little more time to answer this. So, and I see my screen's lagging, so hopefully you can hear me okay. I'm not positive if you can, but I'm hopeful that you can at least hear me. So, let's look at number 3. Number 3 says the Japan Trench off the coast of Japan is part of the boundary between an oceanic plate called the Pacific Plate and a continental plate called the Eurasian Plate. At the trench, bottom, the Pacific Plate is forced beneath the Eurasian Plate, causing earthquakes in Japan. The Japan Trench is an example of which type of crustal feature? Okay, so let's look at our options and then we'll try to talk through it. And if you're just joining us, do your best to kind of catch up with the questions. And we were just talking about the layers of the Earth and the plate tectonics and how that works on the Earth's crust. So we have A, a tectonic plate, B, a mid-ocean ridge, C, a constructive margin, or D, a destructive margin. So the first 2 that I'd throw out right away, A, a tectonic plate. We're not describing a tectonic plate, we're describing a plate boundary. We're also not describing a mid-ocean ridge because it says there is a trench, right? So a trench would be like the opposite of a ridge. So some of that's vocabulary, right? If you don't know that kind of stuff, then you're kind of left to guess. But A and B would be the ones I would throw away, and I would pick between C and D. And remember, these are describing 2 opposite types of plate boundaries, constructive and destructive. Remember which one goes which way? Constructive means new crust is being made, and so if new crust is being made, plates are moving away from each other. Destructive margins are where plates are destroying crust, which means they're moving towards each other. So when they say the Pacific plate is forced beneath the Eurasian plate, that means one plate is being pushed under the other. So what is happening? Is new crust being made, or is new crust being destroyed? New crust is being destroyed, right? Okay. We've got time for at least one more. Let me maybe zoom out and make sure I pick a we talked a little bit about number 4. Which of the following provides evidence that the present-day continents were once one large continent? And it is D, the west coast of Africa seems to fit into the east coast of the Americas. So I don't necessarily want to do that. I want to look at for let's do 6. I think I like 6 better. So 6 says, which of the following is a theory rather than a fact? So remember I talked a little bit about theories, right? Theory is something that can't be proven to be true, whereas a fact is something that can be verified to be true, right? So one of these is a theory, the others are facts. Let's see if we can pick it out. And feel free to message me in the chat if you have your answer, or if you just want to write it down, that's fine. Good. A, the San Andreas Fault is the boundary between the North American and Pacific plates. Fact or theory? Something that can be proven to be true. We'll come back to it. I'm going to read through them. B, a single large landmass called Pangaea existed about 250 million years ago. Fact or theory? Again, is it something that can be proven to be 100% true? C, the Earth's crust is composed of rocks like granite, basalt, and gabbro. Or D, earthquakes often occur along tectonic plate boundaries. So 3 of those things, we have the capacity and the technology to prove our facts. 1 is something that we don't have the ability to 100% say is factual. I may have given this away earlier, so again, this may have ended up being an easier question. Well, the answer is B. A single large landmass called Pangaea existed about 250 million years ago. Again, a theory doesn't mean that it's not true. A theory means it's probably most likely true, but it's something we'll never know for sure whether it was true or not. Theory. It's just an idea that's been verified by enough scientists to say, yeah, that's the science behind the explanation is logical, and so it would make scientific sense that this would be true, but we can't say for sure that it is, right? So that's the difference between theory and fact. All right. Well, if you don't have anything else for me, I'll call it a day for science. Hope that was helpful for you, and I will talk to you all tomorrow. So I hope you have a great rest of your day, and I will see you then. Okay. Thanks, you guys.